This is Lab 2, Motion of a Falling Object. The goal of this lab was to show that the force is acting on the object when it was dropped from rest and it falls slowly. The results of this lab were determined by using an experimental model and two different computational models, one which used just gravity and the other one which used both gravity and drag. Newton's second law was used in order to determine that the net force was not equal to zero. The net force we know was not equal to zero because the object was accelerating. The forces contributing to the net force in this lab were the weight force and the drag force. The physics principles used. As I said, we use Newton's second law. You can derive the momentum principle from that. From there, you can get that net force is equal to change momentum over change in time. We also use the force of gravity, which is equal to negative mass times acceleration due to gravity times j hat, which is the direction of the force. We also use the force of drag, which is equal to b times speed squared times j hat. B is the proportionality constant of drag. We also use g, which is acceleration due to gravity, 9.8 meters per second squared, and this was the mass of the ping pong ball. Now we can get into the experiment using tracker. The origin of the axis was placed at the center of the ball. The axis is slightly tilted in order to follow the path of the ball to the end. There is a meter stick taped to the wall in order to be used as a calibration of length. When looking at the position versus time graph, you can see that it is curved, which notifies us that it is accelerating. Now we can take a look at the computational models. Here we are looking at the computational model only using gravity. Here's the ball's mass, the initial position, initial velocity. Here's the time step, acceleration due to gravity, j hat, which denotes the direction of the force, the proportionality constant. In this case, it's 0 because we're not looking at drag force. Here we use a while loop in order to repeat for each time. This is the final time, which is the same from tracker. Here's the formula for weight force, and net force is only equal to weight force because we're not looking at any other force such as drag force. Here's the velocity update formula, which has F net, which means it is directly related to weight force. The position update formula is going to use that new velocity. When looking at the vector arrows, you can see that it only will display the weight force and not drag force because the drag force is 0 for this model. When looking at the model when run, you can see it follows a similar path to the video and tracker, and only the vector for weight force is displayed. When looking at the position versus time graph, you can see it has a similar shape to the one in tracker. When we look at a comparison of the two graphs, you can see they start off similar, but towards the end they do tend to separate. We can then therefore predict that there is a force acting on the ball in the opposite direction of gravity. So the additional force that we observed was actually the drag force. So now in this next model, we're going to use both gravity and drag force. The first difference you'll see in the code is that the proportionality constant is no longer 0. We found this by looking at the observed final position from tracker. So now the weight force is still going to be used and it's still the same. However, now we're also using drag force. We square it because it's a quadratic. And now the net force has changed, which now it's weight force plus drag force. This is going to impact the velocity update formula as well as the position update formula. As you can see when looking at the bottom, the vectors for drag force is no longer 0. And when you look at the model, you can see that there's now a small red arrow, which indicates that there is a drag force acting on this model. Now comparing all three models, you can see that the gravity and drag force combined is a lot closer and a lot more aligned with the observed position, as they overlap at the beginning and they also overlap at the end. There's only a slight difference in the middle. So the results of the video. As seen, there was a slight difference in the middle of the gravity and drag model and the observed model. However, there was still a closer similarity between those two models than just the gravity model. The reason because of this is the endpoints of the gravity and drag model used a proportionality constant which came directly from the endpoint of the tracker model. Possible differences in this experiment could be because of the position of the tracker points could be wrong due to blurriness in the video. It is also possible that there was a slight updraft since the video was filmed directly next to a door. The what does it mean question? Well, neither model is going to reach the terminal velocity. However, the model with drag is going to come a little bit closer to reaching the terminal velocity, and the model with just gravity will never reach the terminal velocity. As you can see, the vectors are still not equal and the net force is still not 0. So given that the terminal velocity occurs when the drag force and the force of gravity are balanced, I decided to change the code and make the final time later, which allowed it to reach its terminal velocity. The terminal velocity ended up being negative 10.42, as you can see, the forces are balanced and that it has a chance to level it out. When it is at the terminal velocity, the net force would be 0. The answer to the what if question, well, it doesn't matter if the ball is given an initial velocity. The terminal velocity is not going to change. The only difference is how fast it reaches that terminal velocity. When the initial velocity is 0, it reaches that at about 3 seconds. So what I did is I changed the code, gave it an initial velocity, and it reaches the terminal velocity at about 2 seconds.